Okay, so we continue with problem 23. So actually problem 23 here come from the nice textbooks. I just modified the diagram. Okay, so we try this diagram first. You are given this schematic diagram and find the transfer function x1s over ts. Okay. So x1s is here. This is x1s. So sometimes when we have a few components connected, we need to create the displacement. We need to create the displacement, the possible displacement. So maybe in this case, because if you refer to the circuit loops, so when we have another second loop, we must create another current flow. It's the same thing as mechanical system. When we have a third components, meaning that we need to create the second loop, the second equation. So meaning that we need a second displacement. Okay. So in this case, if you refer to the force here, so force to the M5 kg, so we have spring 5 Newton meter connected to the 5 kg mesh. So we have another component, your viscous damper. So this one is your FB, symbol in from the table. This one your spring K. This one is your M. So when we have this kind of system, so in general we redraw again the schematic diagram. So how we redraw again? So this is your M, 5 kg. 5 kg, this is force to the 5 kg, your FT, and then this is your spring connected to your 5 kg M. So in general, after when you have components connected to mass 5 kg, and the other half of the spring should be connected to the either M, or we create the mesh here equal to 0, something that dummy mesh lah. Just imagine that spring must be connected to M, so to body, the to M lah. Okay, so from this one, and then you create the third component here, your FB, and then we go to the wall here. So the idea is to make sure that easier for you to create the displacement. So in this case, these are the displacement x1t, and we know that after the k here connected to the FV, so actually it connected to another m with the value 0. So you create another displacement here. You can create x2, whatever variable, x2. So based on this diagram, so maybe easier to derive the equation of motion. Compared to I give you this diagram and I create here x2t. If you are familiar with the system, we are not create the m0 here, the dummy mesh. So simply you can derive the equation by create the displacement in between a spring and the FV. So actually in between here, we just imagine the dummy mesh. Okay.
Doctor, I don't get
diagram, if you derive the differential equation, or you want to create the free body diagram also can. Okay, so if for free body diagram, if I create here free body diagram, your M is 5 kg, with the displacement must follow the force direction. So force direction here is your Ft. What is the reaction from the components? Must be opposite direction with the Ft. So component itself, if you're 5 kg, 5 kg M, meaning that dx1 over dt squared. Force for M. MA. Your M is 5. So 5 d x1 over dt squared. And then what is the components connected to x1, the displacement x1. So you have the k here. K value is 5. 5 Newton meter, so meaning that you have 5 x1 t. And K also connected to viscous damper Fv. So in this case, connected to M0. So meaning that you have the reaction with the displacement x1. So x2. X2 lah. In this case, the displacement is x2 for the reference x2 here. So finally, if you derive the equation, so we can derive Ft equal to 5 dx1 over dt square plus your k x1t minus x2t. Why? Because your k is 5 connected to another components. So the k here is 5 lah. So we can put 5 here. So we can put 5. 5 x1 minus x2. So you can Laplace at the free body diagram level, or you can Laplace here. You can get Fp become Fs. So Laplace the second order second derivative, you can get 5 s square x1s. Assume that initial condition is 0. And this one 5 constant become x1s minus Laplace x2t become x2s. So this is the first equation that you get. Can you follow?
Doctor, I don't
So for the second equation, the same process, you can look the free body diagram with M0 here. M0. With M0. So if you can create the free body diagram, if I put the free body diagram here, M0, and equal to 0, 0 kg. Actually no M there, but we create the dummy M. So the displacement is x2t. Okay? So you have the component K. Component K reaction from the input from the previous one. So you have K x2t. And minus the K is connected to K x1t. So opposite direction. So arrow here shows the opposite direction. So reaction from the component K. Your component K is actually 5. So you can put 5 here lah. You can put 5.
Doctor, we have a question.
So the 5 x2 minus 5 x1. And you have another component Fv. So refer to the previous one. Fv here connected to M0. M0. So Fv, the value is 4. So 4. So actually 4 dx2 over dt. So refer to the damper Fv. Fv to relate to the displacement. You can get force. So Fv dx over dt. Dx over dt. So finally, if you derive this equation, you can get 5 x2t, actually x2t minus x1t lah, because our reference now x2. The previous one 5 for the spring, x1 minus x2. So you must remember. Plus 4 dx2 over dt equal to 0. No external force. The force comes from the previous component. So if you Laplace this one, you can get f x2s minus x1s, x1t, Laplace become x1s, plus 4s x2 s. Refer to the differential equation, first order differential equation. When we Laplace, they become sxs, sfs. So f, our function is xs here, xt. Come from this one, xt. So this is your second equation. So your equation now, you have two variable, x1 and x2. So refer to the equation. So you have two equations. If you form the matrix, but depends on you. You want to use simultaneous equation. Substitute x1, x2 into x1 for the first or second equation as you can. Or you want to use Cramer's rule. But I think this one is much easier lah. So x1t, x1s, and this one x1. Sorry, x2. So x2. So the first one is x1s and x2 equal to false if the first equation is 0. The first row is the first equation and second row become the second equation. So your output is 1 becomes 0. So if you refer to the previous equation, so this equation, if you put in the matrix format, you can get 5s squared plus 5. Correct? For x1. For x1, you can rearrange, group all the x1 and group all the x2 function. So finally, you can get here 5s squared plus 5. This one is minus 5x2. And the second equation is minus 5x2. The x1, x1 is minus 5. X1 is minus 5. Your x2 is 5 plus 4s. Follow this one lah. Group all the x1 and x2. So meaning that if you multiply again your matrix, you can get the equation 1 and equation 2. Correct? So finally, if you try to get x1s from the matrix using Cramer's rule, you substitute the first column with the answer because x1 is your first column, the first line here, x1. So x1 become fs0 and maintain the second column, 5 plus 4s. Divide by the matrix, the whole, 5s squared plus 5 minus 5 minus 5 here, 5 plus 4s. So you multiply, you multiply here, multiply minus this one. So finally you can get fs multiply with 5 plus 4s. Divide by, so you need to multiply here. So be careful that you have to multiply many variable. Plus 5 and then multiply 5 4s minus, you have minus here, minus 5 and minus 5. So finally, you can get your final answer. Your final, bring the fs here, bring the fs to the left side. So finally, you can get x1s over fs equal to equal to, you have the 5 plus 4s divide by all this one. You calculate, you have to calculate this. You have to calculate the delta. Calculate and rearrange the transfer function until you get the delta is something. What is the highest order here? Order 3 plus what is the variable here? Order 2 plus anything. Combine all the variable S1 plus all the variable S0. So this is the transfer function that you need to derive and get from the system. Any question?
Can you hear us, doctor?
So you also can ask to get the transfer function.
Can you hear us? Yeah. Hello, doctor.
Hello.
I can hear you. I should wearing this one.
Doctor, I have a question regarding the X2. Why do we even have to put the X2 in the first place?
X2?
Yes.
Why we need to put X2?
Yes.
Yeah, because when
No. I mean M2 and X2. Yes, the full block.
M2, what do you mean? This one, M, 5 kg?
No. The other one, the other M, the M equal to 0.
M equal to, this one just we create a dummy, but actually the value is 0.
Yes, but why do we have to assume this?
Because it actually, if you familiar how to derive, how to assign the displacement, it's not compulsory to put the dummy M here value is 0. So if you know that this component spring connected to M, so spring here to connect to the FV, you should have M here. That we call that M0. That's why we create to make sure that you can derive the equation of the system. But if you know without this M0 also, actually we can derive the equation. We can derive this equation. But you must know where to put the displacement. Because sometimes we give you X1 here, but you must know where to create another displacement in the diagram.
So we have to create another displacement.
Yeah, you have to create. So to create another displacement, meaning that you must know where the third component should have the different displacement with the previous one. So 5K here will follow the displacement X1, correct? Because connected to 5 kg. But this component also connected to the third component. So the third component should have different displacement with the first one. We cannot assume that if you imagine your circuit, you have different loop, but you assume that the same current flow. We cannot assume that kind of. So we need to create another current at the different loop. Different loop meaning the third components in this case.
Okay, doctor, what if the FV is connected directly to M1?
Connected directly to M1. So something that we have done before lah.
So no need to create a displacement, right?
No need to create the one. Something that we have created. The first example, the simple one.
Yes.
This one. So, but in this case, you have another component here. I put here, I stop here and connect to the spring, and then finally you have the wall here. Different. Meaning that you need another displacement. If we put here direction to the left. If I put here X1, this one become another variable. And because these two components connected to M. K1, I put K1 and FV connected to M. But in parallel, this one in parallel, but series with the component another K here. So to connect to the K2, this one you should create the M0. M0.
So that means whenever we have more than two components, we have to put displacement between each one.
Yeah. So you must understand lah when we should create another displacement. Okay, so the M0 I described in your schematic diagram. So the idea is actually to make sure that we can derive the equation. So the equation of motion. So you know already previously the example you have M component, M component or something like that. So you have the X2 here lah. So we go to another example. So maybe it's easier for you to understand. This one is different example. So when you have force, force actually we give to the M. So where we should put M here? So in general, for easier for us to create the equation, just put F0 here. So this is your FV. So in this case, you must have the displacement here. You can create another variable. If you use X1 here, so this is your X2. Right? You cannot give directly force to spring or to damper. We apply to M. So that's why you just create the M0, meaning that the spring connected to the M, and the force given here is to the right, to the M equal to 0. So the idea just to make sure that you can derive the equation. But if you are familiar, the M0 is not need to display in your diagram. So in this case, meaning that you have to create the first equation here. You have force Ft equal to your spring here 5 with the displacement x2t minus the displacement x1t. This is one equation. Because your M0, if you can put there, M0 dx2 over dt square also can, but the value is 0. You just straightforward to put the k, your k, x2, because we refer to the now force to the M0 here, displacement is x2 minus x1. Okay, the second equation here, you can derive at the second displacement. So meaning that you have 5, but your displacement is dx1 over dt square. Plus, you have spring 5 with the x1 minus x2. Just simplify. You must put x1t, x2t. Plus, your FV is 4 dx1 over dt. This one equal to 0. We are no external force given to the M5 kg. External force given to the in the diagram to the spring lah, but actually to M0. So meaning that you have this equation. So if you feel that the equation is simple, you can just substitute x1 into the x2 into the second equation. If this one is your first equation, this one is your second equation. So you Laplace the first equation, you can get Ft become Fs 5x2s minus 5x1s. So this is your first Laplace transform. And this one, if you Laplace, you can get 5 s square x1s So every time you do the practice, you remember how to get the Laplace transform for second order or first order derivative. Plus 5x1s minus 5x2s, because our reference is x1, so x1 minus x2, plus 4s squared x1 s equal to 0. So your question is to get the x1 over fs. So make sure your equation must consist of x1 and fs. So you can use Cramer's rule, build up your matrix format and get the x1. Also can, or you can substitute.
Doctor,
Yeah.
why do we have 4s square?
Sorry, not 4s square, 4s. 4s, sorry. Okay, correct.
Okay.
Okay. So you have two equation with two variable. So the final answer, you must have x1 over fs. This is your you want to find this transfer function. So make sure if you use the first equation, you want to substitute into second equation, meaning that from the first equation, you can get x2 equal to what? So substitute the x2 here. So finally, you have the x1 and f. So you can get x1 over fs. So do practice doing this one. Practice substitution or practice using Cramer's rule. Sometimes it's much easier using Cramer's rule. So you can get easier to get the transfer function. Okay, so you do it yourself here. So make sure I think.
Doctor. Okay.
Yeah.
Katanya, I have question. For test 1, we cover until what topic?
Test one, your test one. This is week 4, week 5, week 6. Week 6. So until mechanical. But question is not ready yet.
Until
So
chapter
maybe.
2. Right. Until chapter 2, right?
Yeah, not at the end of chapter 2. Because chapter 2 we have electromechanical. So electromechanical and if you refer to format, hopefully we follow the previous format. Because we are not ready the question now. So if we follow the previous format, the test 1 should include until translational mechanical system. That is the previous format. But if we have any...
So without rotational, Doctor?
Thank you.
Yeah, without the rotational.
Okay, Doctor.
Okay. So you can try this one also. You can try this one. Looks like you need to create a few dummy m. So, but finally you can get what is x2. X2 is given here. X2 over fs. So we have the example from previous example. So hopefully you finally can create the schematic diagram for this system. You have the spring. Between the spring and the damper here, you need to create another M0. So otherwise you cannot connect it to this one. So, and then you have the damper, and then you have the 10 kg M, and then another damper. So meaning that this is your FT. So where to create the displacement? You are given displacement here, and here meaning that here. Here is your x2. They want you to get the x2. So you need to create your own variable to describe the equation of motion for this system. So if between spring and the damper here you have one x2, and you have a damper here 5, Newton second per meter. So you create the third component here, you create this, maybe I can put x1t, and this one also you need to create another maybe x3t. Then, so you can derive your own. You can derive the first equation if I refer to the mx3 here. So your ft become m0, 0 to x3, so you don't have any values, 0. So you have spring 2, meaning that 2 x3t minus x2t. Correct? Spring connected to M0 and M0. So the second displacement X2, no external force. 2, so meaning that you have spring 2. 2 X2 minus X3. X2T minus X3T, you can do your own. So plus 5 also connected to the second M for the displacement X2. 5, what 5? 5 is damper. So dx2 over dt minus dx1 over dt. Refer? The damper F5 here connected to the displacement x1 and also to the 10 kg displacement, x1. M0 here, x2. So when our reference is x2, so x2 minus x1. And the third equation here, 5 kg m. So 5, the displacement, I put x1 there. So dx1 over dt squared. x1, So what components connected to m1? x1. So you have the spring, the damper 5. 5 meaning that dx1 over dt minus dx2 over dt. Our reference x1. So plus another damper is 2. This 2. 2. So 2 connected to 10 kg. 10 kg displacement is x1 over dt minus connected to x2 for the m0. Sorry. F here is x1 only. So at once only. You don't have the connected to the wall. So x1. Can you imagine? So you need to create, this is 2. This is 2. The 2 only connected to 10 kg, so x1.
There's another equation, right, Doctor? Wait, another. For the
Another
weight.
equation?
10
One
kg,
more.
10 kg weight, right?
10 kg. 10 kg. This is not 5 kg, so this one is not 5.
Yeah.
10 kg, 10 kg. Sorry. 10 kg. 5 here is 5 MV. This one is MV. This is MV. That connected to X2 as well. X2T. Displacement X2T. So plus 2, this 2, and we connected to the X1 and the wall here. So 2 dx1 dt. So you have 3 equations here. But with the values they're given there, so I think easier to solve to get the x1, x2 over fs. You try substitute x1 and x3 from these 3 equations. So meaning that what you should do, after you derive this equation, Laplace, first step, this is equation of motion. We call it, this is differential equation of motion. You have dx, dy, and so on. So the second step is Laplace the equation 1 2, and 3. After you Laplace, you can use substitution or use the substitution, maybe the first part, and then use Cramer's rule, or you continue with the substitution until you get your question consists of x2, x2s and fs. The final one must consist of x2 and fs, because finally you want to get x2 over fs. So you substitute x3 maybe from the first equation into the second equation, you get x2. So x2 from the second equation goes to the third equation. So finally you can get only x2 and fs. Sorry, the first equation you have x3, substitute into the second. So the second you have x1 and 2. So substitute x1 into third equation. So you can finally get x2 and fs. So practice this one. If you have any question, you can ask. Okay, any more question?
Yeah, just one question.
Huh.
How do we know that we need to add the mass equal to 0 at k, for example?
Yeah, where we should put the mass equal to 0. When you apply force, actually we apply to body M. So in this case, to create the M here, but the M value is 0. It's not displayed in your schematic diagram. So apply to M connected to spring cannot connect it to damper, so you must create another M, 0. But the value is 0. So in general, if you have the components, any component must have M. Spring or damper, maybe in parallel or whatever, you must have another M. Maybe you only have damper, you must have another M. So you cannot, if you can imagine the system, it's okay. You have another damper and another spring here, also can. But you must know where is the new displacement must be created. So if you create the M0 here, it depends on you lah. If you think that looks like very complex to put M0, you know how to create the equation, it's okay. But if you cannot create the equation because you cannot identify the displacement, so displacement here that you can create. If you create M0, you create the displacement. You have the component. You create the M0, you have another components. So you have X2. You can create another and until the end of the components. So you must create the displacement. We cannot assume that all components will have the same displacement. This displacement will be changed when the component move, the energy move from one component to another component until the end of the component. But the total should be equal to 0 or equal to the force applied to the system, Ft. So the total force equal to Ft. Okay? So you need to practice, otherwise you cannot derive. You need to derive. The diagram can be given any diagram. Okay, the direction of the force, whether the component series or parallel, you give a different value of M, Fd, and so on. But the idea is to make sure that you understand how to derive the equation of motion of the system, and finally Laplace the equation, and you can get the transfer function that whatever you need. If you not familiar, you need to draw the free body diagram also can to show the direction of force and displacement. So finally you derive the equation. You add all the components from the free body diagram. Okay. So we have another example here before we stop. Actually, the same example that previously, but in our case, we are not consider the gravity. If we consider the gravity, that is your project. The project will be considered the gravity. So in our class, we just assume that the effect force from the gravity, we just assume equal to zero. So your equation for the translational x-axis or y-axis, the how to derive the equation still the same. So don't worry about the gravity lah. So in this case, if you refer to this diagram, we applied force to M here. M. So we hang the spring and the damper here somewhere. So if you give M, so your system will be vibrate or oscillate, up and down and so on. It depends on the components involved. So in this case, from previous example, we assume the x-axis, all the x, because x-axis, the movement depends on the force. In this case, because we put the vertical position, so displacement we just assume y, y-axis. So if the displacement goes down, so defer to the force here. But if we give force to M, to the up to M here, so your y displacement should be to the positive direction. And so depends on the force here to the M downwards, so your displacement also goes to downward. So how to derive the equation is still the same. So force given to the system, force. So when you give given to M, so you must create the reaction from M. So M dy over dt squared plus all the components connected to M. So you have Fv, displacement dy over dt. You have the spring K. What are the displacement? Because the total must be force. And unit must be force. So K yt. So equal to Ft. So if you have a few components here, we can make it M here, another M, and another spring, and then you put somewhere here also can. So you can derive your own equation, but refer to the displacement. From M, you have another component and created another M and so on. Alright, so you can practice to do this one. And finally, what is ys over fs? So meaning that you need to Laplace this equation, and finally try to get group all the ys and get the ys over fs.
Excuse me, doctor, can I ask a question?
Yeah, can.
Where is the gravity component?
Yeah, that's why at the first part I discussed, we just assume the gravity is zero in this case.
Oh.
Yeah, to make sure that it's easier to solve the problem. But the real problem, and you can put the gravity in your project. The project, the gantry crane, to how to create the force to lift, lifting process and so on. So we must opposite with the gravity. You include the gravity after this. We can maybe next class after we finish the rotational, and then we can discuss your project for the modeling.
Okay.
In your modeling, your project, we must include the gravity. But for your simple modeling syllabus, we assume that equal to zero. So otherwise, you must create here M. If your movement to follow the gravity, you plus. So meaning that if you have M here, you give it down. So meaning that M dy over dt square plus gravity. GT. The gravity. Meaning that mg lah. Mg. This one based on the displacement. This one is your mg. Unit must be force. Mg is gravity. Mg. So you must add. But if we give force opposite the gravity, give force here, you have m here. So what happened to the displacement y? So you must follow that your m dy over dt minus gravity, mg, because the gravity will be opposite direction with your movement. So you must know that which one must be plus gravity, because to follow the direction gravity. When your movement opposite gravity, meaning that minus force from gravity. So in your class, our modeling, we just assume that this one 0, but actually not 0. We just consider the displacement based on the force given, not based on the gravity. But in your project, you must include. You must include the gantry crane for lifting process. How they move, you must include the gravity in the equation. Okay? Any more question? 12:30. So we finished that. So next class we go to the translational rotational mechanical system. So you can refer to example from test 1. I uploaded the e-learning. You have 3 tests at the previous semesters, so you can practice lah. You can practice. I will give another tutorial from the previous semester. Also, we have the tutorial for the chapter 2. So you can do. Or you can refer to the nice, normalized textbooks. So you have Ogata textbook also. Ogata is very good. You can refer. Maybe different variable they use. They are not use FV, they use B. So B actually the friction here. Ogata, if you refer Ogata, they use B. Or small b. You refer, small b. Different variable, but the same. Okay, any more? Any question? Okay, so before the test, we will discuss the test question. But we state equation. We will go very fast in state equation because we already know that the same diagram, the same schematic diagram we use in the state equation to get the transfer state space representation of the system. Okay? Any more? And so make sure you complete the discussion